Today is going to be 90-2. We're going to take a look at a system of three variables and we're going to solve with them. So we're going to solve a system of equations to those three variables, and we're going to kind of talk briefly about Gaussian elimination, but we're going to emphasize when we're trying to complete these problems the simplified version of this. So given a system of equations, the following moves will result in an equivalent system of equations. So here are the rules for Gaussian elimination and how we can manipulate an equation. The first, we're able to interchange the position of any two equations. The second, we need to replace an equation with a non-zero multiple of itself. And the third, we can replace an equation with itself plus a non-zero multiple of another equation. Now, although that these three rules, adding an equation to one another to create a new one, still applies. Now, these mainly are going to be used when we examine these systems in terms of matrices. Now, we will spend a day in class kind of talking about that, and we're not really going to go in depth with matrices, but we're going to enable ourselves to solve a higher order systems in using matrices to kind of help us do that. Now, the other thing I wanted to talk about was the difference between consistent and inconsistent systems. I know it used this verbiage within the notes and with the homework, but like what did it mean by when it used the phrasing consistent and inconsistent? Now, a consistent means that the system has at least one solution. So like if you found a value for x and y, that works. Or if you got infinite solutions, well, you at least have one solution, and so we say that the system is going to be consistent. Our system is inconsistent when it does not have a solution. So when we got like 0 equals like 5, we said that that was no solution. And it kind of makes sense because this is a false statement, and so it's not consistent because we got a false statement. And so that's the difference between a consistent and inconsistent equations, system of equations. So solving this first one in three variables, here's kind of a set of steps of what I'm going to do. The first step is I'm going to pair one equation with the other two to eliminate a variable, and I want to eliminate the same variable in both. So in this case, I can pair equations 1 and 2 together and 1 and 3 together. So this is equation 1 and 2. This is equations 1 and 3. So pairing the two new equations together and eliminate another variable. So now what I want to do is, now that I've paired these two equations together, I want to be able to eliminate a variable. In this case, I want to eliminate z. Z is really easy to eliminate here, and I can eliminate z in this one. In this case, canceling it out, I get 5x equals 15. For this one right here, I would have to use the rule number 2 for the Gaussian elimination. I can multiply any equation by a constant that's non-zero, so in this case it's 3. So distributing that 3 through, I get 3 times 3x is 9x, 3 times 3y is 9y, 3 times negative z is negative 3z, and 3 times 4 is 12. And so now I can add those two equations together, and so I'm going to get 10x plus 7y equals 23. So now step 2, I'm going to pair the two new equations together and try and eliminate another variable. Well, in doing so, my x is already by itself here. There's no y there. Technically the y variable is already eliminated here because it got eliminated here. So that's done. Solving for this variable though, because I have to know what x is, divide both sides by 5 and I get x equals 3. Then I have to take this 3 and I have to plug it back in. And so I'm going to get 10 times 3 plus 7y equals 23. Minus both sides by negative 30, divide both sides by 7, you're going to get y equals negative 1. And so now I have to take both of these, right? We're working backwards here, and I got to plug them all the way back into one of the originals. I decided to do this equation here. So I got 3 times 3 plus 3 times negative 1 minus z equals 4. Simplify, that turns into 6. Minus 6 on both sides, I get negative 2. Divide both sides by negative, I get z equals 2. And so the solution is going to be the ordered pair where x is 3, y is negative 1, and z is 2. So a quick review on that. The first step that I did is I paired one equation, which is equation 1, with the other two, equation 2 and equation 3. So that's why I had equation 1 and 2, equation 1 and 3. And I eliminated the same variable in both equations. I eliminated z at least. And I multiplied this one by 3 so I can eliminate z. Then step 2, I paired the two new equations together, this equation and this equation together, to eliminate another variable. And so it just so happened that that same variable was already eliminated, which was y, so I could just use this one to solve. Divide both sides by 5 and I got x equals 3. Plug it back in. Step 3, you got to plug back in working backwards, so plugging it back in, 10 times 3, and then solving for y, I got y equals -1. Then I have to take both of those values and I plugged it into this third equation here, even though you can plug it into either of them, it doesn't matter. And so I plugged it back in, and that's how I got z equals 2, and so I wrote the answer as a point. Example number 2, in solving this system, first step, I need to pair one equation with the other two to eliminate a variable. So in this case, it looks like I can pair equations 1 and 2 and 1 and 3 together again. And so I want to eliminate the y, and so this one was really easy. It just cancels out this one. I'm going to have to multiply this top equation by 2, and so I can eliminate y there, adding straight down. That's how I get all those other values. Step 2 is I need to pair the two new equations and eliminate another variable. So pairing my two new equations together, I guess I can eliminate the x here, so I multiply the entire equation by -3, and so that's how I got the -6x here, and then there's a positive 6x there. So adding those two equations together, I get -3z equals 0. Divide both sides by -3, and I got z equals 0. So now step 3, plug back in working backwards. So I have to take this z equals 0 and plug it into one of these equations. And I plugged it into this one. Solving for x, because this is 6x plus 0 equals 6. Divide both sides by 6, I get x equals 1. So then I have to take both of those values and I have to plug them back into one of the originals. And so solving for y, that turns into 4, that just disappears, subtract both sides by 4, divide both sides by 2, I got y equals 2. And so writing my answer, it's going to be 1 for x, 2 for y, and 0 for z. Now in this example here, what I want you guys to do is write it down, put a star in it, and say matrix. Okay? We're going to talk about what this looks like in terms of matrices later on, because this is kind of crucial, or it's kind of important that we examine it this way. In essence, because I only have 3 equations, but there's technically 4 variables, what's going to end up happening is we're going to get a solution that's going to be not x equals this, or x2 equals this, or x3 equals this. We're going to get a dependent system, and we're going to kind of talk about that a little bit more tomorrow. And the reason why I say 4 variables is I have x1, x2, x3, and x4. So I want you to put a star, like I said, next to this, write it down, put a star next to it, and write matrix. So what kind of concepts were discussed today? And then we took a look at a system of equations with 3 variables. What elements were similar to the system of 3 variables and 4 variables? Now I know we didn't really go into it, but what things do you think that we could be doing that could be similar? That's kind of like the way that I want you to phrase that. Now the third example had 4 variables. Now research what a 4-dimensional figure is and share what you've found. This does conclude our lesson. If you guys do have any other questions, please leave them in the comments.